Okay, all right. So, so we will continue our discussion on clustering, and in today's lecture, I am primarily focusing on clustering on graph data as compared to what you have seen in the last lecture. Okay. So before I move on, do you have any question, any doubt from the previous lecture anywhere? If you have any doubt, any question? Okay, there is one small question which I thought that I will need to clarify in little bit more detail. This is about implementation. So there is one thing about the randomization thing in K-means plus, and I think this is little relatively non-trivial if I explain these things in Word. So what I will do after this lecture, I will put a small Python code showing that how to implement that thing in Python or maybe in any other programming language, so that you can actually implement the randomized things. So this will come up again in many times in the course. So I thought that I will need to clarify that one. So I will put up small code post in this MS Team, and you just take a look. And then if you have any doubt, then you can ask me in the next lecture. Okay. So because that is going to be an important thing which will be used many times later in the lectures as well. So that is a small thing from my part. So if you do not have any question, then I will move on to the topics today. So what I am going to do is essentially this again unsupervised learning, in the sense that we do not need supervision. And so I'm going to focus on graph clustering in particular. And so I'm going to focus on three things today: minimum cut, hierarchical clustering technique on graph, and then spectral clustering technique. Okay. So these three things I will try to cover in today's lecture. So let me start off with the motivation, little bit of motivation. So why we should pay attention to clustering graph or network data. Now, typically in literature, graph and network data, typically these terminologies are used interchangeably. Okay, it's just like network or graph data, something like this. So why we really need to solve this problem? So far, I mean, in the previous lecture, I talked about the clustering problem, and the clustering problem on n-dimensional feature vectors. So you can assume that every point is represented in an n-dimensional feature space. You compute some similarity or distance between points, and then you can apply k-means, k-means plus, or there are lots of other algorithms which can actually operate on this one. Okay, you can do and then group this. So final objective, of course, as usual in the previous case, is to group the elements based on some kind of similarity. That's what we really want to do. Okay. Now, what about the following problems? For example, when you have to deal with the Facebook friendship network. Okay, this is not n-dimensional points. Okay, there is some connections between different individuals and things like that. Okay. Think about the communities in question answering website like Quora. Most of you probably have used Quora, and you know there are certain communities. For example, one community devoted to answer questions on, say, for example, machine learning. One community devoted answering questions on, say, data analytics, algorithm design, or so on and so forth. Okay. So every community will have their own structure, and they are essentially defined by how they are actually interacting with each other. Okay. Now the other thing is, other example is protein interaction network. So we have different proteins in our body, okay, in any kind of animal or human being and so on. So how different proteins actually interact, okay, and what's the consequences of that? You can figure that out. That would be very helpful in finding out the cause of different diseases. We can also find out good drugs to treatment and things like that. Okay, so all these situations we really need to deal with the graph data. Okay, and I will show you in a moment few examples of that. But there are lots of other areas and there are lots of other problems where you have to deal with the graph data. This is just some kind of very small number of examples. So here's an example of Facebook friendship network. You know, you have the individuals, okay, as the kind of the nodes in the graph, and the connections you can call this connections a friend. Okay, something like this. So what you have to do given this kind of structure, what you have to do, you have to basically find out, for example, say your cluster. Okay, the clusters that most likely cluster that you belong to, depending upon the connections and so on, your friend circles and things like this. Okay, set of people, those who will share similar kind of things. Okay, that's often the case. And you have seen probably sometimes in Facebook that Facebook is giving some kind of recommendation that do you want to attach yourself with this particular group and that particular group and things like that. So it essentially comes from this kind of community discovery. Okay. So in technical terminology, it's called community discovery. You discover a community, based on that, you can basically identify the nature of the community, what they like, what they dislike, okay, what the other community that they may like. So things like all these kinds of things actually take place inside the Facebook, for example, the system. Now, all we want to do, we of course want to do coherent, we have to find the coherent groups. Okay, for example, friend circles in Facebook. Okay, so essential objective is to figure out the similar objects and simply group them together. Okay, so again, it's a grouping problem. Okay, that's why it is called the clustering and unsupervised learning. We don't want to use any kind of supervision, but using the similarity or the links between them and things like this, you can actually figure out the possible groups. Now, I talked about the protein interaction network. So you can think about this as an example. Okay, there are various kinds of proteins and how they actually interact with interact between themselves and so on and so forth. So if you can identify that, then you can actually figure out. I mean, there are many things in biology. Okay, you can find out new drugs, new medicine for a disease. You get to know and things like this. So the fundamentals of everything. Okay, all these kinds of data. It stands on an abstract structure called a graph, okay, or network. Graph is kind of popular data structure in computer science. Okay, most of you probably know it. We have already taken some basic data structure algorithm course. Okay, so everything that we see, that kind of the problems that we discussed so far, so they can be modeled using a graph structure. Okay, and in a graph structure, there are two main things: a set of objects and a set of connections. So the set of objects are called the nodes in the graph, and set of connections are called the edges in the graph. This is technical terminology for the graphs. Okay. Now in Facebook, if I refer to Facebook friendship network, you can see that individual persons are basically the nodes in the graph and the objects, and the connection, whether I am your friend or not, this kind of connections, okay, is called the edges and things like this. Okay. So essentially, you want to model this one. This is a very small example of that graph, okay, where you can see the edges and nodes and so on and so forth. Okay, this is a node, the edge, and so on and so forth. Okay, it's very simple. Now, there are also various types of graph. For example, unweighted graph versus weighted graph. So in unweighted graph, the edges do not have any weight. Okay, simply they're connected or not connected, something like this. It's a binary relationship. Okay. Something like that. So if you think about your Facebook friendship network, this is an example of unweighted graph. Okay, you are connected to somebody, or not connected to somebody. That's it. As opposed to unweighted graph, in weighted graph, you have the weights of every edges. Okay, so the weight will signify something. For example, if you think about the email communication network, okay, then the weight could mean that how many times two individual communicated over a period of time, say last 1 year, things like this. The number will indicate that. Okay. If you think about city and road network, the nodes will be, of course, the city or the towns or things like this, and the edges will denote the kind of the distance between two cities, two towns, city versus towns, and so on and so forth. Okay, so there are all kinds of graph that we will deal with. Depending upon the problem, we have to actually model this particular thing. It can be unweighted, it can be weighted. All right. So the main attraction point of any graph data is that it shows relationship between objects pairs. Okay, pairs of objects. And so we have to convert this information to find out other kinds of information, interesting things like community and so on and so forth. Okay. So therefore, the concept of centroid, what we have seen in case of k-means, that when we are dealing with the clustering problem, we had some points, some k number of points or some n number of points, and a cluster was represented by a centroid, which is kind of the mean point of all these points. Okay, so that is why it was called the centroid based clustering. But the concept of centroid in a graph data is not very clear. Okay, so what do you mean when I say that the centroid of your Facebook friendship network? It's very difficult to define that. You do not know that. Okay, now it's difficult to define the center of the graph. So when this kind of situation will arise, you of course it's difficult to apply the centroid based clustering technique, something like k-means. You may probably need to convert this into another representation form. The graph embeddings and things will come into picture, but you cannot straight away apply all these things. So there we need specialized algorithms and techniques to deal with this particular kind of situations. And so in today's lecture, I'm primarily going to focus on this kind of algorithms. Let's start with clustering the unweighted graph, and then we will gradually move on to weighted graphs and so on and so forth. Okay. So let's start with the simplest form of things, clustering unweighted graph. And I'm going to do this by introducing a simple concept called minimum cut. And you will again encounter the minimum cut concept later in this lecture. Okay, but this is just the starting point. So let me just define this one. So now that you know what is a graph, edges, and things like this. So the minimum cut is basically partitioning a graph into two disjoint subsets. Okay, you have to partition the graph into two disjoint subsets, say S1 and S2, so that the number of edges between these two sets, S1 and S2, are minimized. So once you partition these two sets, the graph into two sets, then you simply count the number of edges which are basically crossing these two groups. Okay. Now your objective would be to minimize that number of edges. So how can you partition a graph in such a way that you can minimize these edges? Let me just take an example, okay, and then illustrate what is actually happens. So if you consider this particular example. So I have this graph of 8 nodes, okay, and this is what the minimum cut looks like. Okay, you can figure out that A, B, E, F is one group. C, D, G, H is another group, and the number of edges which are actually crossing these two groups actually 2, because there are 2 edges crossing these two groups. So the minimum cut value will be 2. Okay. It's difficult to find out other partitions where you have the minimum value 2. In this case, you do not have that situation. Okay, that's basically the min cut problem. So our objective would be to find out the minimum cut from a graph data, simply because you want to, again, I would like to go back to our older definition of clusters and groups and things like that. You want to maximize the within group similarity or relationship, but you want to minimize this between group similarity or relationship. That's what you want to do. Okay, and that's why it is called the minimum cut problem. Okay, now let's move on to the clustering using minimum cut. Okay. So the broad steps are something like this. Okay. Inherently, the minimum cut algorithms will find two groups from a big graph. Okay, it's inherently like that. It basically splits into two. Okay. So often you need to find out more than 2 groups in any real life application. So what do we do? So you can use a minimum cut algorithm to break a graph into 2 sets, say A and B. Okay. Now then again you can take these smaller parts, you can apply the minimum cut, break these smaller groups again into smaller groups and so on and so forth. And you simply continue until and unless you impose some kind of stopping criterion. Okay, it depends on you, okay, when you want to stop it. So it's kind of a splitting approach. You start from the big graph, you split it and so on. Okay, and then simply stop some point when you think you are in a good position. So for this purpose, The algorithm that I'm going to discuss now is called Kargar's mean cut algorithm. So it was invented by MIT faculty David Kargar. Okay, so it's a very simple algorithm, efficient, but it's a randomized algorithm, something like what we have seen in case of K-means. And I will show an example to illustrate how actually things actually run, okay, with detailed steps and so on later on. But let me just tell you the basic idea, the fundamentals of this algorithm. Okay, so what's the fundamental? The key principle or the key technology that this particular algorithm uses is called age contraction. Okay, you take the nodes and simply contract the edges between them and so on. Okay, and so I will explain in a moment with an example. Don't worry about it. So what you do, that you pick an edge at randomly pick an edge. Okay, and then collapse its two endpoints because you have chosen one edge, then there will be two endpoints of this edge. So collapse its two endpoints into a single node. Okay, and you simply proceed in this way again and again and again. Okay, seems like a very abstract description of the algorithm, but when you see the actual example, things will be very clear. Okay, so let us see how it happens. So say this is my graph, the same old graph that I had taken in the previous slide. Okay, so I had 8 nodes and a bunch of edges and so on and so forth. So I would like to figure out the minimum cut, partition this graph into 2 so that there are minimum number of crossing edges between two groups. Okay. Now, the first step of my algorithm, as I mentioned, is that you randomly choose one edge with a probability, with the associated probability. Okay, and then wait. So in this case, okay, if you randomly choose, so what is the probability that the edge BC will be picked? Okay, so can anybody answer? If you randomly choose one edge, what is the probability that edge BC will be picked?
1/14.
1/14. So there are total number of how many edges are there? 14 edges there are?
Yes, sir, there are 14 edges.
Okay, all right, yeah. So in the very first step, if you choose any like one edge, the probability that it will be picked randomly is 1/14. That's absolutely right. Okay. So again, you run some random number generator, and I will, as I have promised, that I will after this lecture I will send you a small code to make sure that you know what I mean. Okay. So, but for the time being, you say that your random number generator, you are using some random number generator to find out a random number or some probability value, and then you're going to pick out these things. Okay. Now say that you pick edge BF with probability 1/14. Okay, that's the first thing that you're going to do. All right. So now what happens is that you have to contract the edges. The principal idea behind this algorithm is called edge contraction. Okay, so you have to contract these edges. So you have to contract the edge B and F. Okay, so how does this happen? So if I contract this, this is something is going to happen. Okay, so you're going to put B and F together. The moment you have chosen one particular edge, you are going to put the two endpoints of this edge into single node, which is called, like, you can call it super node or something like this, okay, or hyper node or something like this. So BF becomes a single node now, and you can see now that there are parallel connections between A and BF and E and BF, simply because that originally there was an edge between A and B and E and F. Make sense? Do you have any question? Because this is the key to this algorithm. Okay, if you understand this, it's very clear, the rest of the steps. Does anybody has any question? All right, okay. So assuming that you do not have any question, let me move on to the next step. Now, let me just ask you another question. What is the probability that the edge EBF will be picked? Yes, please. Hello?
1 by 11.
1 by 11. Why it is 1 by 11? I'm talking about the age EBF.
2 by 13.
2 by 13, yes, you are right. 2 by 13 because there are two parallel edges between E and BF and total number of edges is 30. So the probability that age E and BF will be chosen 2 by 13. That's absolutely correct answer. Okay. So now again we have to choose one particular age with some probability, associated probability, and say that I am going to pick this age 1 by 13, the age GH, because the probability that the age GH will be picked 1 by 13. Now I am showing these steps for the purpose of demonstration. Okay, but when you write a code, which age will be picked, that will be determined by your random number generator. Okay, that I do not know. But because I have to kind of show you, so I'm basically showing it this way. But don't assume that this is the deterministic things is going to happen. Okay, nothing like that. All right. So then I'm going to put together G and H together. Okay, I want to contract this age and then do the same kind of thing. So if I do that, then something like this is going to happen. And I hope you agree with me that this is going to happen. Okay. Now the same technique. Okay, I apply. I have to choose a particular age with a probability associated with it. So say I now next choose is D and GH, of course with probability 2 by 12. Where there are two parallel edges, there are total 12 edges, so I can do that. Okay. And so we are going to contract the whole thing again, something like this. Okay, put together, we are going to get something like this. Okay. Now again, I repeat the step of selection of the age followed by contraction. So if I choose this age A and E, of course with probability 1 by 10, and then I contract this is something going to happen. Okay. Then again I have the same thing. Okay. Say I choose AE and BF with probability 4 by 9. You're going to get this kind of stuff. Okay. Finally, I can choose, for example, CDGH with probability 3 by 5, and I'm going to get this kind of thing. Okay. So that's the end point of my algorithm. The moment I got two super nodes or hyper nodes, okay, so I'm basically done. So this is my partition of the graph. Okay, so what's the partition? One side I have ABEF in one group, in another side I have CDGH in another group. Okay, so this is basically the mean cut. And what would be the value of the mean cut? Or rather, I should not say mean cut, but the cut value actually. The mean cut has to be minimum, so it doesn't guarantee the minimum value, but anyway. So the cut value in this case would be 2. Okay, because there are two parallel edges, okay, crossing these two groups. Okay, that's basically the minimum cut value. So you stop when you have two super nodes, okay, after several steps of contraction, selection, and so on. Okay, you stop then and you get the graph partitioning and so on and so forth. Okay, so in this case the value is basically 2, the cut value. I should not say minimum cut, I should have said actually the cut value. Any question from anybody?
So, so how much does the first edge that we select, because it is not it is not exactly deterministic, like we are allowing for random selection. So how much does that affect the final result?
That's a good question. Yeah. So this is true for any randomized algorithm. Okay, because every step you are taking some random decision, and that is why I mentioned that this algorithm does not guarantee that you are going to get minimum cut value. It does affect the way you choose it. Okay, but then when you are, so the primary reason that I am talking about this particular algorithm is it is very efficient. Okay, it's very efficient. It runs on very large scale efficiently, unlike the other minimum cut algorithms and so on and so forth. Okay, now the question is why I should take this up, even if I know that there is randomized things can go wrong and things like this. And I would like to give a little bit of intuition behind this one. Okay, it's always difficult to explain everything intuitively, but I will try to give it and see whether that helps you. So the fundamental idea, okay, in this algorithm is that you are going to choose a particular age with the associated probability. Okay, if the probability is very high, then that it is highly likely that you are going to choose that particular edge. Now, when probability can become high, think about a particular edge. For example, think about the top right side graph. Okay, there are 4 edges, 4 nodes: AE, BF, DGH, and C. Now, in this case, highly likely that AE and BF will be chosen. I mean, the most probable, okay, situation that AE and BF will be chosen. Why? Because there are too many edges between them. Okay. So what does this actually signify? It signifies that AE and BF has, these two nodes have too many connections. Okay. Now, what does that mean? Too many connections means they are closely related. What does this mean? That you want to consider them in the same group. Okay, you want to put them into the same group. So that's the essential intuition behind this algorithm. Okay, so that's why you basically want to choose probabilistically. Now, and you have rightly pointed out that there is no guarantee, and I completely agree with you, there is no guarantee. So in order to safeguard that little bit, not entirely, but safeguard a little bit, what you should do, because this is a randomized algorithm, so for good results, what you do, you run this algorithm multiple times. Okay, that means it will produce multiple cuts, then take the cut with the minimum value out of all this. So to some extent, this can address the problem that you mentioned, but of course doesn't guarantee that. Any question?
So just one more question. So
Sure.
So what would be the point of clustering graphs? Like I can understand for the n-dimensional points, but like could you explain, like in a friends network, why would we want to do clustering? Okay,
all right. So think about the product advertising. Okay, say for example, Apple iPhone 13. Okay, newly launched. Now Apple needs to sell this product, they need to advertise this whole thing and so on and so forth. Okay. Now if they know that a particular group has affinity towards this product and so on and so forth, they can actually send. For example, from Facebook group circles, they can mine this data and they can basically send this information to that particular group. Okay, and then they can like take benefit out of this particular situation. Okay, you just tap the group behavior. And depending upon that, you can apply this. Make sense? Okay. Any other question? So graph clustering is a very interesting and important topic actually. It's always evolving, and because of this connected data now, like all kinds of social network, this and that and so on and so forth, everything is connected now. So this is even becoming much more important than it was before. That is why there are tons of graph algorithms, okay, fast, slow, exact, random, the approximate, all kinds of things, okay. A whole lot of things in this case. All right, any other question?
So how do we define the stopping condition that you had mentioned?
So your question is related to this particular algorithm or in general?
Sir, in this particular one.
Okay.
Like suppose
All right. Okay, I will answer to your question. All right. So in this case, this is deterministic. You stop when you see you have two nodes. Rather, I should say two super nodes, because in this case, one node means that there are several basically smaller nodes in it. So yeah.
Sir.
Yep.
What if this graph has 3 clusters connected via 2 min cut values? What if there are like 3 separate chunks of these smaller graphs? For example, if there would have been another connected subgraph, what would its outcome be?
Okay, I think your question is what happens when you have to find out more than 2 groups, right?
Yes, sir.
Yeah, all right. So I briefly mentioned in one of the slides. So what you do basically, if you want to apply this particular algorithm, then what you do, you basically take the you initially got 2 groups. Okay. Now you can apply your algorithm again on these smaller groups, and then split it again further. Okay.
Okay, sir. Sir, and is it guaranteed that we will get these two groups, for example, in this case, is it guaranteed that we will get these two groups whether we choose the edge AE first or edge BF first?
Could you please repeat your question? I couldn't get it very clearly.
Sir, since it's a randomized process, so it's
Right.
not guaranteed that we'll get the same solution for all the cases, right? So
No, you cannot guarantee that. Yeah, that's right. You can't guarantee that.
so then how are we supposed? So how do we like guarantee that this is the correct answer? And
Okay, so see, there are many algorithms, and the reason I tell you why I have chosen this particular, and you will get to know the other algorithm later on in this lecture. Okay, so this algorithm is very efficient, as you can see. Okay, it's very efficient. Now, this is good for when you have to deal with very large graph. Okay, very large graph. Okay, you can basically efficiently run it. Now, you are absolutely right when you are saying that because of the random decision, I cannot guarantee the optimal solution. Okay, but in any case, when you will be dealing with very large graph, people hardly bother about the optimal solution. They will be very happy with the suboptimal solutions. Okay, which is I think close to the optimal solution, but not exactly the optimal solutions. Okay, now the fact that you are choosing the edges based on the likelihood of this based on the probability of being picked, okay, depending upon the number of edges between them and so on and so forth, that actually enhances that possibility that you're going to get good solution, not the best solution.
Hello, sir.
Yeah, please.
Sir, if we want to cluster into K clusters,
Right. What you should do?
hello, sir. If we want to cluster into K cluster, can we assume that the stopping criteria has K number of nodes as a stopping?
So in this algorithm, so you mean the K number of super nodes, the hyper nodes, that means that you get at the end of this algorithm?
Yes, sir. Finally, if we get K nodes, then can we
Right.
assume that that's a problem?
Yeah, that's the final criterion which you can use. But only thing is that you cannot get this in one go. Okay, you first get two, then you take maybe the bigger one, then split this into two, and so on and so forth in this way. But in single run, you cannot get that because inherently this is like the bipartition algorithm. You get two partition from the bigger graph.
So from two partition, again we have to do another partition
Right.
in
Exactly.
either of the nodes. Okay.
Right. That's how it can proceed. Okay.
Sir,
Any other questions?
Excuse
Yes,
me,
please. Sure, sir.
sir, in this question, for the end condition, do we have to check both the condition for that the two nodes will have to be there for as super nodes and the min cut value has to be, matlab, it has to be there, and if we had multiple edges connected to that, then we would not have that a specific min cut value.
Uh,
Because for example, there are three nodes connected to someone just asked a question that what if we stop at k nodes connected, then it may be possible that two of them are connected with a 2 min cut value and one with a 1 min cut value, so that we won't be having a specific min cut value, so we would not be able to stop, right?
well, I'm not sure whether I understood your question correctly, but let me try to answer your question. So your question is about, I think, when to stop and the possibility that sometime you are going to get 3 edges crossing and sometime 2 edges crossing, and which one you want to choose. Is that your question, if I understand your question correctly?
No, sir. My question was regarding when we have k separate subgraphs and some sections are connected with, for example, 2 min-cut values, and some sections are connected with 3 min-cut values. So that would be like we won't be able to stop at that point if we want to stop at k min-cut, for example, k subgraphs or k supernodes, as someone pointed out. I was just
So see,
clarifying this.
this algorithm is inherently, so you have a big graph, you find 2 subgraphs at every run.
Yes, that
Okay.
that was my question. So we have to stop at most 2, right?
Right. So yeah, exactly. You cannot get in one go like all k subgraphs. You cannot get that. Okay. Any other question?
So once we run the this algorithm several times, how do we sort of how do we take one result out of it? Like, if you understand what I
Okay,
mean.
so it's very simple. So you run this algorithm. So in every run, after every run, you are going to get 2 things: the 2 hyper nodes and the associated cut value, right? 2 things you are going to get.
Yes.
So if you run say n times, then you are going to get n such things, and simply choose the one with the minimum cut out of this and corresponding hyper nodes.
Okay.
Okay. Any other question? All right. Thank you for all the questions. That was very entertaining for me. All right, so let me move on to the next topic. So what I have discussed so far, clustering unweighted graph, like whether there's a relationship or no relationship, kind of binary thing. But now we are going to deal with weighted graph. Okay, and the algorithms I'm going to talk about is pretty popular in the literature. It's actually old and popular. Okay, so let's try to like take a look at like these basics of these algorithms. So the algorithm we're going to talk about is hierarchical clustering algorithms. There are broadly 2 ways one can do it: agglomerative and divisive. Okay. So in agglomerative, you have the bottom-up approach. What you do, you start with each object being a single cluster. You can consider that each object belongs to a single clusters, and then you go by margin. Okay, you took the two best, like the individuals can be grouped together depending upon their proximity. You simply merge it and simply proceed it this way. So by margin, start from one and then gradually you merge it and make bigger clusters. That's basically agglomerative one. Now, the divisive clustering is completely opposite. It takes the opposite view, that you start from the whole thing. Okay, just take one and then simply you divide it in smaller parts and so on and so forth. Okay, that's how you can basically do it. Now, the example of divisive clustering algorithm you have seen in the last few slides, which is the minimum cut-based approach. And this is one such example. Okay, this is a different way of looking at the things. Okay, but this for the same objective. So the good thing about this is that, unlike k-means, it doesn't require the number of clusters in advance. Okay, in a situation like where you have to figure out that you do not know that number of good clusters and so on and so forth, this is actually a good thing. But of course, there should be some stopping criterion. Okay, which you cannot avoid. So one stopping criterion could be based on the distance threshold. So essentially, you are going to merge together, right, 2 groups. Or you are going to split a bigger group into 2 groups and so on and so forth. So there could be some proximity or similarity or distance and things like this by which you are actually doing all this stuff. So you can, instead of telling that I want to create k clusters, you can actually look at those thresholds and then say, okay, once the threshold is higher than the smaller than things like that, so you can basically stop. So for today's lecture, I'm going to focus on hierarchical agglomerated clustering, not the divisive one. Okay, so I don't want to divide, I want to merge people. So that's the simple reason. But anyway, simply because this is simple things, simple to understand, simple to implement, and things like this. And it's almost everybody uses this when somebody has to use clustering and so on. Okay, so So the broad steps is something like this, that you need to have a similarity function. Okay. In any clustering problem, you need to have a similarity function which will determine that how close two groups to individuals would be. Okay. So you need to do that. So first you start with all instances in a separate cluster. Instances means the samples, individual objects in separate clusters. Then you repeatedly join the two clusters that are most similar. Okay. And so on and so forth. So you basically, that's why you hierarchically proceed. One step, lower step, then step, and so on and so forth. And because you are basically hierarchically proceeding in this approach, then you can actually remember the merging steps. Okay, how you are going to merge this. The first two, then these two with the third one, then these three with the another three, and so on and so forth. So the history of this merging, how you are going to merge, okay, one step after two step after three step, and so on. So this is called, standard technology is called dendrogram. Okay, the dendrogram will give how actually you created the merging steps. All right. So the important question, what's the important question we have to deal with? The important question is that how to determine the nearness of clusters. Essentially it depends on the merging, the idea called merging, and you have to determine that how I'm going to merge. I'm going to merge based on nearness. Okay, two groups will be merged together if they are very close to each other. Okay. Okay. So broadly, there are three different variants: single link, complete link, and average link. Okay. So in single link, and I will show examples. Okay, don't worry about it. Okay, I'm just telling you the basic idea, and then I will take concrete examples to demonstrate. So in single link, what happens is that the distance between two groups are considered based on the closest points. Okay, that means a single link. So if you have 5 points in one group, 6 points in another group, and so distance between these two groups will be considered by computing the closest point. That's it. Okay, this the most like I would say the good tie between all pairs of individuals and so on. Now, in complete linkage, the distance is computed based on the farthest points of two groups. Okay, it's a different viewpoint, and you will get to know why these viewpoints are actually taken, the benefits, and so on and so forth. And the average link, you know, as you know, is the middle ground, not closest, not farthest. You consider the distance between all possible pairs of things or elements between two groups, and then take the average value between all this. Okay, so broadly the three possible approaches. Now let me just define with an example the similarity, the notion of similarity for single link. Okay, and then I will move on to the complete linkage one. So as I mentioned, we are dealing with two groups containing some number of points. Okay, and I have the pairwise distances of similarities and so on. Okay, and now I have to figure out the distance between two groups. Okay, or similarity between two groups using this information. Now say my cluster 1 or my group 1 is containing 2 points I have shown here. My group 2 is containing 2 points here, and so on, and the numbers indicate similarity. Okay, higher it is better. All right. So now my question is that the similarity between cluster 1 and cluster 2. What would be? I need to compute the final single value. Okay, the similarity between two clusters. So what would be that based on the complete linkage, single linkage definition? So it would be sorry. So the numbers are actually distance, not similarity. Sorry for the mistake. So numbers are actually distance. Okay. So the distance between cluster 1 and cluster 2 would be 3. Okay. Because this is the most similar object that you can think about. But there is no other thing smaller than this one. Now come to the other case. So now if I run this algorithm, say I have this data point. Okay. So there are 8 points. Okay. And I want to apply the single linkage algorithm to form the clusters. Okay. So what will happen? Now, first the individual points will belong to individual clusters. So all 8 points will be in all 8 different clusters, and then I'm going to merge this gradually. So the very first step would be that I'm going to merge these two because they're the closest one. Okay, I'm going to merge them together. Now the next step, I'm going to merge these two together. Okay, because among all possible pairs, I can see that they're closest and so on and so forth. Now the third step, I'm going to merge this one. It seems that the distance is like smaller than the right side, so I'm going to merge this one. Then I'm going to merge this one together. Okay, all right. Now again, I can again merge together with different clusters, form bigger groups and so on. So it seems that that next this group will be merged together. Okay, because if you consider the distance between all possible clusters in this case, it seems that these two groups have the closest distance. So I'm going to merge this together. Okay. Next, I can merge together. Okay, and then I can find out the final one by merging everything together. Okay, so you can see the hierarchy of the cluster development. Okay, from smaller circle, the bigger circle, the bigger circle to bigger circle, and so on and so forth. Okay, so you can always find single one at the end of it, but then you have to stop somewhere. So you can basically say that, okay, when the distance threshold is higher than this, okay, I will stop. I am not going to form any other clusters. I'm not going to merge together and so on and so forth. So this way you can stop. All right. Okay. Now let's look at the problem with the single link. Seems like a pretty simple idea, but for any pretty simple idea, you have some problems associated with it. Okay. So what's the problem? The problem is basically chain or elongated clusters. Okay. You get chain or elongated clusters often. Okay. And what does that mean? Assume that you have 4 points, something like this, okay, sitting there. Now, if I apply single linkage clustering algorithm, I'm going to merge these two first together, okay. Then I'm going to merge these two first, then, okay. Then I'm going to merge this and so on and so forth, okay. So essentially, because the definition of the proximity or similarity is defined by the closest pairs, okay. If 2 points, only 2 points are related, 2 points from 2 different groups are related, you are going to put together all points from 2 different groups. Okay, because they are defined by similarity between only a pair of objects. You are not taking into consideration all objects in the groups. That's the problem. Okay. And so what essentially you're going to get that the 2 points which are very far apart, one in extreme left, one on extreme right, but still you are putting together only because they are connected via some other points in between. Okay, and so this phenomenon is called elongated clusters in single linkage clustering problem. Okay, so you can have very long chain. Okay, from left to right, you probably will find out that there is no relationship at all between the extreme left, and extreme right, but yet you put together simply because of the intermediate points actually driving this cluster. Okay. So that's the major problem with the single linkage clustering technique. And in order to solve that, we can actually apply the other clustering technique, this which is complete linkage clustering technique. Okay. So I think we can take a break, and after this break, we can come back and then discuss about other clustering techniques.